Now let's take a look at our second problem. So this problem is a more general case of a problem you have previously had in your homework. So the problem is as follows. We are given n packages. Each of these packages have a deadline di, which we need to deliver the package before that time. And delivering each package takes time ti, takes ti number of days, for example. And if we deliver this package before the deadline, we'll be given some pi money. So mainly what you had before was that ti was equal to 1 for all of your packages. And again, as before, at each time we will be delivering only one package. So if I deliver package with deadline t with which would take t days, then that would take me t days, and I will not be able to send any other packages in the meanwhile. So our problem is that given a set of n packages, we want to send these packages such that our profit would be maximized. Now, before moving on to the dynamic program, let's make an observation. So assume that S is a set of packages that for which I know it can be delivered on time. So like all the items in S can be delivered on time. And well, when you have such claim, it means that you have some ordering on packages such that if you send them in that order, then they will be all delivered before their deadlines. Now I'm claiming that in such case, I can deliver all these packages in the increasing order of deadlines. So I will first send the package with the earliest deadline, then the one with the second, first, and so on. So we are going to use an argument like the swap argument we had before in your in the scheduling problem we had seen previously. So the argument is as follows. Assume that you are delivering these packages according to some order. So first you're delivering package 1, then 2, and so on. Now assume that at some point you are sending some package di, some package I, such that its deadline is after is after the package with deadline di plus 1. So assume that at some point we have such thing. Now what we want to show here is that we can change the order of these two. So instead of sending the one with the later deadline, we're going to send the one with the earlier deadline first. And we want to show that that will not harm our ordering, that will not make us late for any of the packages. So assume that I'm at time S, and at this time S, I will be sending package I originally. So originally you've been sending these packages in some manner, such that you wouldn't have missed any deadlines. And assume that at time S, it's turn for package I. So you will send it. It will be delivered at time S plus Ti. And then you'll send package I plus 1, and it will be delivered at time S plus Ti plus 1. Okay? And again, we can assume we don't have any idle time, because that even if we have, we could just cut it out. Now let's see what will happen if we deliver item I plus 1 first. So here we will deliver this, and we'll deliver it. It will be delivered at time S plus Ti plus 1, and then we will deliver the other package. Okay, so I know that originally when I was sending package I first and then package I plus 1, I was not violating any deadline. So di has to be after S plus Ti, and di plus 1 has to be after S plus Ti plus 1. Now that I made this swap, okay, first of all, it is clear that I'm not violating the deadline of package I plus 1, because, well, I'm sending it earlier than I used to send, so, and I wasn't violating the deadline then, so I'm not going to be violating the deadline now. But what's important here is to note that I'm not going to violate the deadline of package I as well, because now I'm sending it sometime later. But now have in mind, so in the previous ordering, I was sent that I was not violating the deadline of package I plus 1, right? So S plus Ti plus 1 now has to be less than Di plus 1, right? So the point where I would have delivered package I plus 1 is before the deadline of package I plus 1. So this point is less than D of I plus 1. Now I have assumed from before that D of I plus 1 is actually less than D of I. So when this time is less than Di plus 1, because of this relation here, it has to be also less than Di. So it shows that the point that in my new ordering I will be delivering package I is not going to be after the deadline. So I'm not violating the deadline of package I either. So this all can come up to the conclusion that when I'm given a set of packages which I know can be delivered in time, I can just send them in the increasing order of deadlines, and that would also be fine. So this is the conclusion that we needed from this part. Now let's try to come up with a dynamic program. So as usually goes with dynamic program subproblems, we are going to, at each iteration, restrict ourselves to a certain part of our packages. So now I will write this, and by this I mean now I'm only considering packages. So now consider an ordering of deadlines on the packages, okay? So assume that we have this relation on our packages. So when I say D of I mean that I'm considering only packages from I to N, right? And in addition to that, let's consider an S. So S is the time at the moment. So basically D of I and S is going to give me the maximum profit that I will be making if I am to deliver packages I to N, given this ordering here, when I'm starting at time S. So D of I and S is the maximum profit I can make by delivering packages I to N when I'm starting at time S. Now let's see how I can fill this up here. So here's what's going to happen. I'm either going to be picking package I and delivering it, in which case I will be getting, so it would go take the maximum between two things, and so I will be either delivering package I, in which case I will get the profit PI, and then I need to call what? So I have delivered package I was before considering I to N packages. Now I have to consider I plus 1 to N packages, right? And well, I need well, my time changes because I have decided to deliver this package. So this would be my new time, right? I have to spend time Ti in order to deliver this package. So here's whatever I get. But have in mind that if you decide to deliver the package, you need to check that this time S plus Ti is actually less than the deadline of Ti. So here we need this additional condition that S plus Ti is before the deadline of I. If it's not, then it's not possible to deliver package I. But the other case is that I don't deliver package I, so now I again have to consider packages from I plus 1 to N, and my time will not change because, well, I haven't spent any time on delivering any packages. So this would be our recursive relation here. Either I decide to deliver a package I, in which case I will get this, or I decide not to, in which case I will get this. Now let's take a look at our base cases and how to fill this up. Okay, so for the base case we can either consider I as n, or we can consider as n plus 1. Will not make much difference. So if I set this as n, and if I set this time as s, so here what I will need to do is, well, I will check if I have only one package to consider. I have only package n. I will see if this package n can be delivered in time. So you should check if s plus t of n is less than or equal to d of n. If so, then this value would be p of n, and it will be 0 otherwise, because then it means that I cannot deliver this package anyway. So this would be your base cases. Now, okay, so assume now that I've filled up all these top problems. Now, what should I return as the answer? So I need to be considering all packages. So I need to be starting from package 1 to package n. So I need a 1 here. And I need some time here. Now, what is the latest time that I might be delivering something, right? So I was assuming before that I had this ordering on my deadlines, right? Now, have in mind that considering times after d of n really doesn't make sense, because, well, that means you have passed all the deadlines. So you don't really need to consider deadlines after that. So this would be what you need to return in the end, right? So by this 1 here, I will be considering all packages, and by this, I'm considering the latest possible time that I will be delivering anything. So this would be what we need to return. And now let's take a look at how much running time does this dynamic program take. So updating at each iteration of our recursive calls is only constant time, because I'm just taking maximum between two values. So I now need to consider the number of subproblems. So this is what we had. Well, this I can be changing between 1 and n. And just as we argued before, this s really doesn't need to be anything more than the last deadline, right? Because after that last deadline, well, we don't really need to consider anything anymore. So our runtime would be just the multiplication of the two. It would be this, which I think in the question d of n is mentioned as t. So this would be our runtime. Please send me emails if you have any questions about this problem or the previous one. Thank you.